The condition began to develop in the early hours of Thursday, March 14th, across a network of 17 high-rise office buildings in Midtown and the financial district that shared a common building management system platform administered through a centralized cloud-based control interface. The software had been deployed incrementally over the preceding 18 months as part of a coordinated modernization effort intended to optimize HVAC efficiency across multiple properties managed by the same facilities consortium. At approximately 4:47 a.m., a routine firmware update was pushed to the pressure control modules governing air handler units on floors above the 40th story in each building. The update contained a revised algorithm for calculating optimal static pressure targets based on outdoor temperature, wind speed, and occupancy projections derived from access card data. The algorithm incorporated a correction factor intended to reduce energy consumption during low occupancy periods by allowing greater pressure variance between zones. Within 90 minutes, pressure sensors in the lower mechanical spaces of 8 buildings began reporting readings that diverged from baseline values established during the previous winter. The divergence was initially small, ranging from 0.02 to 0.04 inches of water column, well within the tolerance bands programmed into the alarm thresholds. No alerts were generated. The air handler units continued to operate according to their updated instruction sets, modulating damper positions and fan speeds in response to the revised pressure targets without triggering any supervisory override. By 6:15 a.m., as the first wave of building engineers arrived for morning rounds, the pressure differential between street-level lobbies in the exterior environment had begun to exceed normal parameters in 4 buildings, including a 58-story tower on 6th Avenue and a 72-story structure near Bryant Park. The lobby spaces in these buildings were designed as transitional pressure zones, maintained at slight positive pressure relative to the street to prevent infiltration of unconditioned air, vehicle exhaust, and particulate matter. The target differential was typically 0.05 to 0.08 inches of water column, sufficient to create a subtle outward air current at door openings without imposing excessive force on door mechanisms. The building management system logs from this period show that supply air volumes to the lobbies had increased incrementally over the preceding 2 hours, with total airflow rising from the standard 12,000 cubic feet per minute to nearly 18,500 CFM in the 6th Avenue building. The increase occurred through a series of small adjustments made by zone controllers responding to temperature sensor readings that indicated cooling demand, though outdoor temperatures were recorded at 41 degrees Fahrenheit with light winds from the northwest. The dampers serving the upper floor return air pathways had simultaneously begun to close in coordinated response to the firmware's interpretation of reduced occupancy signals, restricting the volume of air being drawn back through the vertical shafts and creating a hydraulic imbalance within the building envelope. The first documented instance of door operation difficulty was logged at 6:52 a.m. by a security supervisor attempting to exit through the main revolving door at the base of the 6th Avenue Tower. The supervisor's report, filed through the building's internal maintenance request system, noted that the door required unusual effort to push and that the rotation felt sticky, despite no visible obstruction or mechanical binding. A maintenance technician dispatched to examine the door found no defects in the bearing assembly, drive motor, or threshold seals. The technician's work order, closed at 7:18 a.m., attributed the condition to possible wind loading and recommended monitoring. At 7:31 a.m., a similar report was filed at the Bryant Park building, where an incoming employee described the revolving door as pushing back with enough force to require both hands to initiate rotation. By 7:45 a.m., 3 additional buildings in the affected network had logged comparable observations, though in each case the doors remained functional with increased effort. Pressure readings in these lobbies now ranged from 0.14 to 0.19 inches of water column above exterior ambient, approximately double the design target. The building management system continued to interpret these readings as within acceptable operating bounds, as the alarm thresholds had been set at 0.25 inches to avoid nuisance alerts during high wind events or when multiple exterior doors were opened simultaneously during peak traffic periods. Between 8 and 8:30 a.m., as occupancy levels rose toward normal business day density, the pressure imbalance intensified in a feedback pattern that had not been anticipated in the system's programming logic. Each arriving occupant who entered through a lobby door temporarily relieved the pressure differential, allowing a brief equalization with the exterior. The building management system's occupancy sensors registered these entries and increased supply air volumes further to meet the projected climate control demand for the incoming population. However, the return air pathways remained constricted by the partially closed upper floor dampers, which the system had not reopened because the occupancy signals were interpreted as localized to the lower floors during the morning arrival period. The net effect was a progressive accumulation of conditioned air in the lower third of each building, with pressure differentials climbing above 0.20 inches of water column in 6 buildings by 8:45 a.m. At the 6th Avenue Tower, the pressure had reached 0.27 inches, and the revolving door at the main entrance exhibited sufficient resistance that building security personnel began directing arrivals to a secondary entrance on the west side of the lobby, where a pair of hinged doors appeared to operate with less difficulty. This diversion went unreported to the engineering staff until after 9 a.m., when the secondary entrance also began to show increased resistance, and one of the doors failed to latch properly after closing, remaining partially ajar against the outward pressure of lobby air. The physical forces acting on the doors at this pressure differential can be understood through basic calculations of force distribution across surface area. A standard commercial entrance door measuring 7 feet in height and 3 feet in width presents approximately 21 square feet of surface area, equivalent to 3,024 square inches. A pressure differential of 0.27 inches of water column, which corresponds to approximately 0.01 pounds per square inch, generates a total force of roughly 30 pounds distributed across the door surface. This force acts perpendicular to the door plane, either assisting or resisting opening depending on the direction of the pressure gradient. For an outward opening door where interior pressure exceeds exterior pressure, this force supplements the door closer mechanism and can cause the door to slam shut with abnormal speed unless manually restrained. For an inward opening door, the same pressure differential adds 30 pounds of resistance that must be overcome to initiate opening, in addition to the force required to operate the latch mechanism and overcome the door's inertia and closer spring. At 9:17 a.m., an employee at the Bryant Park building sustained a minor hand injury when an outward opening stairwell door closed with unexpected force, pinching 2 fingers between the door edge and frame. The incident was logged as a workplace injury report, but was not immediately connected to the building-wide pressure condition. At 9:34 a.m., building management at the 6th Avenue Tower received the first call from a tenant office on the 47th floor reporting that the floor's main entry door could not be opened from the corridor side, effectively trapping 6 employees who had arrived early inside their suite. The floor-level door obstruction represented a separate manifestation of the same pressure imbalance, occurring at the boundaries between pressurized elevator shafts and corridor spaces. The stack effect in tall buildings creates a natural pressure gradient driven by temperature differences between interior and exterior air, with warm indoor air rising through vertical shafts and creating negative pressure at lower levels and positive pressure at upper levels. This effect is most pronounced in winter months and is typically managed through careful balancing of supply and return air volumes at each floor, along with the use of barometric dampers and pressure relief paths. The firmware update had altered the pressure control strategy in a way that amplified rather than compensated for the stack effect, particularly in the upper thirds of the affected buildings. Elevator shafts, which normally operate at near neutral pressure relative to the floors they serve, had become positively pressurized as the supply air volumes increased and return air pathways constricted. At the 47th floor of the 6th Avenue Tower, the pressure differential across the tenant suite door was later calculated to have exceeded 0.35 inches of water column, generating approximately 45 pounds of force holding the door closed against its frame. The door's panic hardware, designed to unlatch with a maximum force of 15 pounds applied to the push bar, functioned correctly, but the pressure force exceeded the ability of the individuals inside to physically pull the door open against the frame seal. A facilities technician arriving at the floor at 9:52 a.m. was able to open the door from the corridor side, where the pressure assisted the opening motion, releasing an audible rush of air as the pressure equalized. By 10:15 a.m., building engineers at 3 of the affected properties had independently begun to suspect that the door operation difficulties were related to abnormal pressure conditions rather than mechanical failures of door hardware. Portable manometer readings taken at multiple lobby locations confirmed static pressures ranging from 0.22 to 0.31 inches of water column, well above the design targets and approaching the levels typically associated with temporary pressurization during fire alarm conditions when smoke evacuation systems activate. The engineers initiated manual adjustments to the building management system, reducing supply air volumes and opening return air dampers to relieve the pressure buildup. These adjustments produced immediate local relief in some areas, but created new imbalances in others, as the interconnected nature of the ventilation systems meant that changes in one zone propagated through the ductwork to affect adjacent zones in unpredictable ways. At the Bryant Park building, an attempt to reduce lobby pressure by decreasing ground floor supply air volume resulted in a reversal of pressure in the lobby, creating a negative pressure condition that caused the revolving door to become difficult to exit through, as occupants now had to push against an inward pressure gradient. The building's chief engineer, recognizing that manual adjustments were producing unstable results, contacted the building management system vendor's technical support line at 10:47 a.m. to report the anomalous behavior and request guidance on reverting to the pre-update control logic. The transition to manual operation stabilized the pressure conditions, but did not immediately restore normal door function, as the pressure differentials that had accumulated over the preceding 6 hours dissipated slowly through leakage paths in the building envelopes. Pressure decay rates varied by building based on the tightness of exterior wall construction, the number and size of operable windows, and the extent of unintentional air leakage through elevator shaft walls, utility penetrations, and other envelope discontinuities. In the most tightly constructed buildings, pressure differentials above 0.15 inches of water column persisted for more than 40 minutes after supply air volumes were reduced, during which time door operation remained noticeably affected. Logged entries in the building management systems from this period show gradual normalization of pressure readings, with most lobbies returning to target differentials between 1:30 and 2:15 p.m. 3 buildings experienced a secondary complication when the sudden reduction in supply air volume caused interior temperatures to drop below the heating set points, triggering calls to tenant services regarding inadequate climate control. The engineering teams responded by gradually increasing heating water flow to perimeter heating zones while maintaining reduced air volumes to avoid reestablishing the pressure imbalance. By 3 p.m., all 17 buildings in the affected network had been returned to stable operation under the restored firmware version, with pressure differentials within design ranges and door operations reported as normal. Post-event documentation compiled over the following week included detailed reviews of building management system logs, sensor data plots showing pressure trends across the event timeline, and incident reports filed by tenant services, security personnel, and engineering staff. The analysis identified a total of 43 documented instances of door operation difficulty across the 17 buildings, including 12 cases where doors required assistance to open, 8 cases where doors closed with abnormal force, and 23 general reports of unusual door behavior. No structural damage to buildings or door assemblies was recorded, and the single reported injury was classified as minor with no lost work time. The vendor issued a technical bulletin on March 21st describing the firmware conflict and recommending that future pressure control algorithm updates include verification testing against stack effect compensation routines under varying outdoor temperature conditions. The facilities consortium's internal review noted that existing alarm thresholds for pressure differentials had been set based on emergency pressurization scenarios rather than normal operation, and recommended that monitoring thresholds be reduced to detect abnormal conditions before they affect building accessibility. The review also documented that the affected building's design specifications assumed maximum sustained lobby pressure differentials of 0.10 inches of water column under normal operation, with a safety margin of 0.15 inches before door operation would be significantly compromised, margins that had been exceeded by factors ranging from 1.5 to 2.1 during the peak of the event.